Robin Hood Radio welcomes you to David Freeman's Science Insider with your host, the senior science editor of the Huffington Post, David Freeman.
Good evening, everybody. Welcome back to Science Insider. Earlier this week, I attended a fantastic talk about asteroids at the Museum of Natural History's Hayden Planetarium in New York City. And it was given by Dr. Amy Mainzer, who is director of the principal investigator of NEOWISE, which is a NASA mission to hunt asteroids. And after the talk, I was ready to rush up to grab Amy and ask her a few more questions, but she was completely mobbed. So I decided I would bide my time, and so now Amy's agreed to, for the next half hour, she's all mine to answer some questions. So welcome, Amy.
Thanks very much. It's great to be here.
Okay, well, thank you. So in your talk, you talked about something which is really fascinating. About this time last year, astronomers and astronomy buffs were all excited about an asteroid called 2012 DA14. And that was an asteroid is an asteroid about the size, half the size of a football field, and it was going to give Earth a very close shave. In fact, the calculation showed it was going to come about 17,200 miles within the surface of Earth. And that sounds far away to us, maybe, but in astronomical terms, that's incredibly close. And as a matter of fact, it was so close, it was going to go below the orbits of some of the GPS satellites. And so all its attention was focused on 2012 DA14, and then all of a sudden, it was no longer a lot of interest. Why? Tell us why that is, Amy. What happened?
Right. Well, 2013 was actually an extraordinary year for asteroid science. And really what happened was, as you mentioned, 2012 DA14 passed beneath the ring of geostationary satellites that surrounds the Earth. Now, this was an asteroid that was discovered roughly a year before its very close shave with the Earth. And it was known, after astronomers observed it very, very carefully, that it was not going to impact the Earth. There was zero chance of that. However, it was known that it was going to get very close. So the world was really watching that. All the astronomers were very excited about it, amateurs and professionals alike. Everybody was really paying careful attention to this object, trying to get measurements of it, to understand more about what it was made of and its size and its shape and so forth. And while that was happening, at the very same time, another asteroid, a completely different object from a completely separate orbit, just a completely separate object entirely, basically smacked into the Earth with no prior warning. And nobody knew that it was coming in advance. Now, this is a very small asteroid in terms of asteroid sizes. This is a really pretty small object. It was something like about 17 to 20 meters across. And so that's kind of roughly the size of a small house. So, it's basically house-sized, if you will. And what happened is when it smacked into the Earth, it exploded in the atmosphere about maybe 10 or 20 kilometers up in altitude. And it was the shock wave that basically broke a lot of glass, and it injured about 1,600 people. Fortunately, there were no fatalities.
This was over Russia, right? Chelyabinsk, Russia. And
right.
As you said in your talk, people saw or heard this, ran to the windows and were standing there, and when the shock wave hit, some tens of seconds later, all the glass shattered, and that's how most of them got injured, right?
Yeah, that's right. And it was actually quite a bit more than tens of seconds. What happened was people saw the flash of light, and it made a brilliant contrail in the sky, just like, when a jet passes overhead, it leaves a contrail. But imagine that instead of hearing the sound wave, a few tens of seconds like you would with a more low-altitude object, this really took about a minute and a half between the flash of light and the shock wave hitting the Earth. And
right.
That's how people know that it was a very, very high-altitude airburst, not something that impacted the Earth at a much lower height above the surface.
Right, and there were videos of this all over the web at the time. How fast was the I guess at this point it's a meteor when it's in the atmosphere, how fast was it going when it hit?
Well, typical speeds for meteors when they impact the Earth's atmosphere are about 20 kilometers per second. So that's kind of around 40,000 miles per hour or so. So it's extremely fast. And that's why even something that is as small as the Chelyabinsk fireball was, that's why it was able to produce such an enormous amount of damage because, basically these things are traveling at cosmic speeds. And when they smack into the Earth, they have an enormous amount of what we call kinetic energy, the energy of motion.
And as someone asked during your talk at the planetarium, what would have happened if it had, instead of giving us a glancing blow, if it had come straight down directly into the Earth? What would have been the result of that?
Right. So this was an object that entered the Earth's atmosphere at a relatively shallow angle. And so it wasn't coming straight down, as you mentioned. Because of its shallower angle, less of the energy made it all the way down to the ground, and more of it dissipated harmlessly in the upper atmosphere. Obviously, if the objects come in with steeper angles of incidence, then more of the energy has more of a chance of making it to the ground. And so there could have been more localized damage.
But is there any, can you give us a sense of it? I mean, I think people who worry about asteroid impacts think of things like the movie Deep Impact, where it was, an extinction level event, they called it. What sort of devastation might have occurred, do you think, if it had come straight down?
Right. It's a little hard to say. So astronomers are actually working on modeling exactly that question so that we can try to give a better answer than just kind of a back-of-the-envelope sketch. But one of the things that's interesting about this particular impact event is that it's so incredibly well studied. People have, literally thousands of cell phone videos of it, security camera footage of it, and not only that, we know the detailed topographic map of the region, and my colleagues, some of them, have actually gone out and surveyed where the blast wave damage was, where was the broken glass, exactly how far did the blast wave extend, and with these detailed pieces of information, now they can start to back out things like exactly how big was the impactor, what would have happened if it had come in at a shallower angle. I mean, the sort of qualitative simple answer is, of course, if it came in at a steeper angle, probably there would have been worse damage. But to answer the question precisely, you actually need to go and do some pretty sophisticated calculations. So they're working on that now.
Right.
And that's one of the reasons why this is such an important event, because we have so much more information now than any other event that's ever happened, really. I mean, usually these things, we only see, little bits and pieces of them coming into the atmosphere, very tiny little pieces. Or for the bigger impact events, all we have are the fossil records, essentially, the craters, the remnants in geology, and that's all that's left. But this one was truly unique.
But you said we have all this information. I know that's one of the things you're involved with, and I want to ask you about that too. But how is it possible that this big, dangerous meteor, there was no warning of this? Why wasn't it seen? Why wasn't it known about?
So the main thing with this one, and the difference with 2012 DI-14, which was known well in advance, about a year in advance, this particular object, in its final incoming approach trajectory, came from pretty close to the sun. So it came out of the daytime sky, and all of our current suite of asteroid surveys, they really mostly operate at night, of course, because they're visible light telescopes, all but one, which we'll talk about in a minute. And these telescopes, it's like trying to observe the stars in the daytime sky with your naked eyes. You can't see them. The sunlight is too bright. It scatters in the atmosphere. The glow of the atmosphere, essentially, the blue sky is just too bright to see the stars.
Right.
So that's why this thing wasn't observed. It just happened to come from a bad direction for people who are looking for asteroids.
So, but ultimately this was kind of a wake-up call, right? I think the fact that this asteroid here, that we didn't know about it really was a wake-up call for scientists to make them think that maybe the risk of an asteroid impact was higher than they thought it was. Is that correct?
So a couple of things about this. It is certainly very difficult for astronomers to say with certainty when the next impact will happen, because these are pretty rare events. It's kind of like predicting earthquakes. We know that they happen on what I would call geological timescales, very long timescales. And, I'm in California, for example. We know that there will be a big earthquake at some time in the future, but it could be, 10,000 years from now. On geological timescales, that's short, but on the timescales of human life, it's really long. And so the asteroids are kind of similar in that they're very rare events. And so we're trying to predict them on very short timescales. And that's statistically hard to do with great accuracy.
Right.
So what this does point out is that it's certainly worth, basically expanding our observational network to look for these objects, because if we don't know where they are, we really don't have much of a chance to do anything about them. But on the other hand, the good part about this is that this is a quite solvable problem, and it's certainly something we can do something about. The other piece of good news is that a lot of the work has already been done to put in the infrastructure to observe and track and characterize the objects.
Well,
And
let's talk about that in a minute.
That's what NASA's been working on.
I want to ask you, I know that's really what you're working on, but let's back up a bit. And as you started your talk about the difference between meteors, asteroids, meteorites, there's still some confusion about that. Can you set people straight? What's the difference between those different kinds of space rocks?
Sure. Well, the main thing is they're all space rocks. And really the only difference between an asteroid, a meteor, and a meteorite is really just what happens to it. So an asteroid is a space rock that's in space and hasn't had any kind of entry into the Earth's atmosphere. And if it makes it into the Earth's atmosphere but doesn't make it to the ground, we call it a meteor. But if it does make all the way to the ground, if we can recover pieces of it, we call that a meteorite. It's all the same stuff. It's just a space rock. It's just a question of what happens to it.
So this fireball was an asteroid. It hit our atmosphere, at which point it became a meteor. It basically disintegrated because of the interaction between the atmosphere and the material, and then it showered down meteorites onto the Earth, correct?
That's right, yeah. So this particular object is what we call an airburst or a fireball, where the vast majority of the energy of impact is dissipated high in the Earth's atmosphere. Basically, as soon as it encounters a little bit of air resistance, it blows it apart.
Well, let me ask you a couple of other more basic questions. First of all, sure. I'm curious about the naming of an asteroid. The 2012 DA14 is a kind of an awkward-sounding name to a layperson. I know there was another asteroid that was in the news last year. It was QE2, but it had nothing to do with the Queen Elizabeth ship or the English monarch. How are these things named?
So the naming process is basically, it's a scientific naming process that's designed to kind of help us keep track of these things, and it reflects the state of our knowledge about an object. So when something is first discovered, we give it what we call a temporary name, a temporary designation, and that's basically the year plus the month of discovery plus, the number of the object that was discovered that month. So, for example, 2012 DA14 was discovered in the year 2012, and it was from the first letter, that D, that indicates that it was discovered early on in 2012. And then the rest of the digits basically are just incremental, they're just counting. So once we know an object's orbit really, really well, we've observed it quite a lot, and we can predict where it is going to be at any given time with very good certainty, then it gets what we call a permanent designation. And it's basically given a number. Right now we're up to, 600,000 asteroids that are known, including mostly main belt asteroids. About only 10,000 of those or so, or 10,500, are what we call NearEarth objects, ones that get particularly close to the Earth's orbit. And so when you get a permanent designation, you get a long number. And at that point, the discoverer has the right to submit a name suggestion for the asteroid to the International Astronomical Union, who then basically votes on the suggestion and either grants it or denies it. And there are rules for how these things are named. I mean, if it's a main belt asteroid, you have pretty broad discretion in what you can name it. But if it's a near-Earth object, there are some special rules that apply. You can't name it after a living person. It's supposed to be a mythological name. So most of the NEOs, or near-Earth objects, I should say, are named after our gods and goddesses.
So you mentioned the asteroid belt. What are asteroids made of, and where are they? Where do they come from? Tell us about the kind of natural history of asteroids.
Right. So most of the asteroids in our solar system live in what we call the main asteroid belt, which is basically a region between Mars and Jupiter. And like I said, there are 600,000 of them known today, and that's probably a small fraction of what's really in the main asteroid belt, which could be many millions of objects. So they were formed a long time ago, and these objects have stayed there in the main asteroid belt for billions of years. Since they were formed. So basically, these are kind of the leftover bits and pieces from the cloud of gas and dust that originally collapsed to form our sun and all of the planets. And, the asteroids and the comets, these are sort of the remnants. These are the little bits and pieces that just didn't get swept up by the planets. So they're kind of the dust bunnies of the solar system, if you will. And they're still there. And most of the time, they just stay right there and don't go anywhere.
If the solar system lasts long enough, ultimately those will coalesce and form new planets?
It's pretty unlikely that would ever happen. And that's because Jupiter in particular is just so massive. It's such a huge planet. It really exerts a tremendous amount of gravitational influence over the asteroid belt. And we think that in some ways the tremendous gravity of Jupiter is enough to really keep those little pieces from ever really coagulating together. it certainly hasn't happened in 4.5 billion years, and my guess is that it probably wouldn't happen going forward either.
So these are billions of years, 4.5, 5 billion years old for the most part, or for all of them. Is that the case?
That's right. These are really old objects, and they have had some things happen to them in the intervening time. They've sometimes collided with other asteroids and broken into little pieces. So people might remember the old asteroid game from Atari. You remember that one? And you basically had to blast an asteroid, and then it would break into a lot of little pieces. Well, that really is how it works. If an asteroid collides with something else, it tends to make a lot more small fragments than big fragments.
Well, yeah, and I want to talk about that in a minute because that has to do with how we might protect ourselves from an asteroid impact if one is on a collision course. So, and these things vary in size greatly, right, and in terms of their composition as well.
That's right. They have widely varied compositions. They have widely varied sizes, everything from, mountain size. The largest asteroid is Ceres, which is sort of roughly the size of Texas, all the way down to, tiny little grains of rice that are still out there. Now, the thing is that most of the asteroids are in the main belt, and they stay there stably for long, long periods of time. But occasionally, every now and again, some will kind of leak into the inner part of the solar system where they can get into the region that gets close to the Earth. And when that happens, these things, kind of one of three things happens to them. Either they get pulled into the sun, or they have an encounter with a planet that sort of kicks them back out again, away from the region near the Earth, away from the terrestrial planets, or they can smack into a planet. And that's what we think happened with the Chelyabinsk meteor. Basically, it sort of made its way in from the main asteroid belt and eventually got onto a collision course with the Earth.
So it may have left the main asteroid belt how long ago?
It's difficult to say. Now, one thing we know about near-Earth objects is that compared to the main belt asteroids, they don't last very long. Now, it's still a huge amount of time on human timescales, maybe tens of millions of years, but that's a lot less time than the asteroids have been in the main asteroid belt, which is usually billions of years. Mm-hmm. So basically what happens is that when things come into the near-Earth region, they just don't tend to stay there very long. They tend to get pulled into the sun, like I said, or they collide with the planet, or they get kicked back out. Now, that's fast for an astronomer, right? Tens of millions of years is what we would call a short time scale, but of course it's long on the time scales of human lives, and that's what we care about, as people who live on the Earth.
Earth is being hit all the time on a daily basis, is it not?
Yeah, that's right. The Earth is constantly getting bombarded with tiny, tiny little pieces, and of course we see these as shooting stars. These are very small objects. They range in size from, kind of sand grain size to maybe rice grain size. If you see a really bright shooting star, it's probably only the size of about a rice grain or maybe even a pea. So there's a lot of this teeny tiny bits and pieces of sort of pocket fluff, if you will, that is constantly raining down on the Earth. But most of it, just impacts harmlessly in the upper atmosphere. We see a little bright light, and that's it.
So what exactly is being done to protect, well, let me ask you this, what is the risk? I know it's difficult to calculate, maybe there's no number, but are there any numbers about the way to quantify the risk of an asteroid impact, a serious one? And what is being done to safeguard the Earth, if anything, from a potentially very cataclysmic event?
Well, the good news is that a lot is being done, and this is how we know what the risk is. Like I said, it's a little hard to predict precisely, but we have some general ideas about it. So the good news is that NASA has created a pretty good network of astronomers, both amateur and professional, and also the computing technology that we need to calculate the orbits and look for any incoming approaches. The way this works is basically NASA has what we call the NearEarth Object Observations Program, and what it does is it sort of funds this whole area of research and provides the resources for astronomers to go out and look for these things. It basically encompasses several different survey programs. So these are basically kind of modest-sized telescopes that are constantly watching the skies, looking for anything that's new that's coming in, and also one space telescope, which we can talk about in a bit, that's working in infrared wavelengths with a heat-seeking telescope. Now, these observers are supported by a whole network of people who are following up their discoveries to try to make sure we can really nail down the orbits and know where these things are going precisely. The astronomers submit all of their observations to what we call the Minor Planet Center, which is basically a clearinghouse for all of the observations. And what they do is they take these observations and they basically fit them all together, and they look and see which objects they correspond to and whether or not the new observations coming in represent new asteroids or comets.
Right.
Once they have that, once we have an orbit, the orbits come to JPL, the observations come to JPL, and at the Jet Propulsion Laboratory here, we also have a program that basically does the detailed impact calculations. And so they are constantly looking and constantly watching to make sure that there are no close approaches that we don't know about.
And I know there's a class of asteroids that NASA calls potentially hazardous. How many are in that or classified as potentially hazardous, and are there any that seem to be at this point on a collision course with Earth?
Right. So the potentially hazardous subclass of near-Earth objects, this is basically a type of near-Earth object that gets really close to the Earth's orbit. The technical definition is it comes within 0.05 astronomical units of the Earth's orbit. Now, an astronomical unit is the distance between the Earth and the Sun. So this is something that comes within 5% of that to the Earth's orbit. Now, it doesn't mean that the asteroid and the Earth are ever going to be at the same place at the same time, which is what a collision requires. But it means that they're a population that we really want to pay attention to. We think that there are, in total, something like 4,700 of these that are larger than about 100 meters across. And of those, we think that only about 25% have been discovered so far. Now, like I said, there's good news, and then there's more work we got to do. In the good news category, the NASA-funded surveys at this point have firmly established that we have found and tracked more than 90% of all the near-Earth objects that are larger than 1 kilometer across. So these are the objects that are really capable of causing global extinction-level events, like the one that killed the dinosaurs.
And that's the one 65 million years ago that struck Yucatan. How big was that one? Do we know how big that one was?
Yeah, they think that this one, this so-called dinosaur killer asteroid, was probably about 5 to 10 kilometers across, so really big, mountain-sized. And so now what we've been able to do, NASA was actually chartered by Congress to do this in 1998, to go out and find 90% of all the 1 kilometer and larger near-Earth asteroids. And that's been accomplished now. We've shown that that's been done. So that's the great news. That means that, it's really hard for there to be something out there that's that big that we don't know about. Right. There are still a few percent that are not found yet. So we have more work to do on the really big stuff. But it's a huge reduction in what we know about the risk, because now we know that there isn't something really big. It's very unlikely that there's something really big lurking out there that we haven't already seen.
So we don't know if there's nothing that NASA scientists or that you're worried about coming our way.
Nothing in that size range, no. Now, for smaller objects, that's where the picture is a little less rosy. And what we've been finding to date is that with our telescope, we've used this infrared space telescope called NEOWISE to basically characterize a representative sample of the population that we can use to figure out what we think the whole population looks like. And from our research, what we have found is that we think that down to about 100 meters across, so this is sort of football field-sized objects, which are still capable of causing a lot of regional damage. Now, remember, Chelyabinsk was only about 20 meters across, so these are still very large asteroids, not extinction-level events, but big enough to cause regional damage. In that size range, 100 meters and larger, we think that about 25% of them have been discovered. So that leaves the vast majority that still remain to be found. And when you get down to sizes as small as Chelyabinsk, it's perhaps a few percent.
And part of the reason these things are so hard to see, in addition to the possibility they're coming from the direction of the sun, is that I think you described them as sort of lumps of coal. What's the kind of chemical composition of these things, and why are they so hard to see?
Right, they're hard to see for a number of reasons, but you brought up an important point. We know that some of these objects are what we call stony, and these are things that have basically got compositions that are, kind of a mixture of different mineral types, but they tend to be brighter. They tend to be a lighter color. These are easier for visible light telescopes to spot because they're brighter, right? So if you're seeing sunlight bouncing off of the surface of such an object, you're seeing, pretty much if it's naturally a lighter color, it's just going to be easier to see. But we also know that there is a class of objects that are out there that are called carbonaceous. And we think that these are dark. They're covered with kind of a sooty layer. It's possible that some of them are actually dead comets that have had all of their ices burned off at this point because they've made many close passes by the sun. And these carbonaceous objects tend to be very dark. because of that, for a visible light telescope, which is, again, seeing sunlight that's bouncing off the surface, they're just dim. They're harder to see. They're fainter than an object that's stony. So what we've been trying to do is basically use an infrared telescope, this NEOWISE project, to characterize the population. Because it's a heat-seeking telescope, we can see things that are both bright and dark equally well, because we're sensing the heat coming off of them, not the reflected sunlight now. And that's what we can use to characterize how many are bright, how many are dark, what fraction of the population is harder for the visible light telescopes to find. So that's what we've been
let's say you find a very large asteroid that seems to be headed on a collision course. Could anything be done to intervene, to stop it, to protect the Earth?
Yes, absolutely. And, one of the reasons that we do these surveys is that the goal is really to try to find things well in advance of any collision event. As my colleague Don Yeomans likes to say, the best thing you can do is find them early, and find them early. Right? Those are the best three things you can do to deal with potentially hazardous asteroids. Because if you find an object when it's, say, 10, 20, 30 years away from a close approach or an impact event, now you have lots of time to deal with it. It takes less energy to move it because it's farther away. You also have more time to prepare many different types of options for mitigation.
Well, excuse me, but when you say energy, the energy required to move it, what would we do if we found a big one? What would NASA or what would the different space agencies do to stop an asteroid impact?
Well, it entirely depends on how much time you have and how large the object is and what it's made out of. So I would say that there's not necessarily a one-size-fits-all answer to that. But it's certainly true that having more time gives you more options and requires less energy to deflect the object. It's kind of like Aikido. You want to be able to just step out of the way without using a lot of energy, right? You want to use the least amount of energy. So if you have more time, it takes less energy.
But does that mean setting up a missile to blow it up? Does it mean setting some sort of a beam of energy to deflect it? What would be involved?
One of the things that NASA has already done is a mission called Deep Impact. And this is where they basically set up an impactor that smacked into a comet. It basically collided with a comet. So it's just something simple, like even this sort of kinetic impact approach could turn out to be very effective and could work very well. It's probably going to depend a lot on the circumstances if we were to find such a thing. You've got to know, quite a bit about the asteroid, what its composition is. You'd like to know that. And, of course, you need to know its orbit. And really, it's going to depend on how much time you have. Think of it this way. If you have 30 years before any close approach, that's going to give you a lot more flexibility and options than if it's only a matter of a few days. We
have only about a minute left. I want to ask you a quick question. I know that in addition to presenting danger to the Earth, there's also an opportunity here. There are people who are talking about mining asteroids, and there's a company called Planetary Resources which wants to ultimately bring asteroid minerals back to Earth. Do you think that's a realistic thing?
Well, I have to say my main interest as a scientist is in trying to protect the Earth from asteroid impacts. So my main interest is in really trying to find, characterize, and track the objects. And what I would like to see happen personally is for us to expand our observational networks. And we're working on a proposal to do that, the NearEarth Object camera. The idea is basically to enhance our ability to find and track them, including objects that come out of the daytime sky like Chelyabinsk. And for me, that's probably where the future lies.
Thank you so much. It was really a pleasure talking to you. I've been talking with Dr. Amy Mainzer from JPL, who was one of NASA's top asteroid researchers, and it's been a real pleasure. Thank you very much.
Thanks very much. Great to talk to you.
Science Insider with David Freeman, the senior science editor of the Huffington Post, produced in cooperation with Robin Hood Radio, robinhoodradio.com on the web.